So I went pretty old school here, old school chemi with the column revamps here. Let me ask you a couple questions right before I start. How many of you here have had safety? Just you guys? Steps? Yes. How many of you think when you look into your chemical engineering future, do you see yourselves going into industry versus, say, graduate work or something like that?
And just is this for
like,
industry?
Yeah, like Dow Chemical, ExxonMobil. Okay, so roughly half. Okay, so that's roughly what I expected. So I'm just going to give a little background on what I mean by a column, and if this doesn't look exciting, you probably should get comfortable with it because it's in your future. And then I'll just talk about a little bit about why I think it's important. This concept, not a concept, but the practice of column revamping. So columns are a primary piece of equipment in chemical separations processing. So if you look at humidification, stripping, absorption, and distillation being the big one, you really can't have them without the tower or the column. And prior to 1970, most work revolved around grassroots, building them from bottom up, brand new towers everywhere, because these type of processes are sort of the bread and butter of classical chemical engineering. After 1970, because of budgetary reasons and everything else, all the workload shifted to revamping existing columns for different purposes. Maybe they were going to perform a completely different operation. Maybe they needed to achieve greater performance, or needed to just be maintained. 1970 was a while ago now, and they're still in use. So there's two types of revamps. There's the internal and external, and for the most part, it's pretty self-explanatory. This is just a picture of operators or engineers actually working inside of a column, and apparently people get pretty freaked out the first time they go in there. I don't know, maybe you could envision yourself there someday. And this is just to show the external really includes the ancillary equipment, which is all the stuff a column doesn't work, in and of itself. So you have heat exchangers, reboilers, condensers, valves, fittings, and all that sort of stuff that is all existing in and around and, making the column work the way it needs to. So you can have internal, external, or both happening. It really depends on the purpose of your revamp. So trays and packing, this is what you're going to find inside your column. And it's either or. So as far as trays, it's pretty much you're going to have like little ring shelves that are welded to the inside of the pressure vessel, and set upon them are things that you would imagine to be trays. It's really exactly as it sounds. They perform best in high pressure separation processes. The packing, you have some different options. They work better in low pressure situations. The structured packings, there's a couple examples here. Random packing being analog saddles and pawl rings and things like that. They're just kind of thrown in there, and then, everything sort of washes over those. The idea with separation being you have liquid coming down a column, vapor moving up. I should say that since maybe you guys know or don't. And you're trying to get the maximum intermingling between those two streams. So why revamp a column? It's exactly as I suggested. I'm sure you could have guessed. You're going to replace old, corroded, broken parts. You're going to maybe have the desire to improve your separations, get better recoveries and purities, or both. Increase capacity. This can be done by, say, if you have packing materials, you could use a more efficient packing material, and when you do that, you decrease the amount of flow that you need, and so that allows them to increase the flow overall. Reduction in energy consumption, so you can imagine those might be useful. So here I'm going to start talking about, it seems like a pretty straightforward, common sense sort of process, why you would do it and everything like that. But there's actually a lot of considerations and layers of complexity when you go to attempt this process. And it's a very common process. If you become a classical engineer, you go to work in a plant, it's something that you could very, very well come in contact with. So for mechanical considerations, I'm going to use more of a specific example. when you have, here's just, basically a schematic that really highlights the area, the portals that you have access between the outer and inner shell. And if you are repurposing a pressure vessel like this, you may have a different optimal feed height that you need to use, or you may need to move a manhole for logistical reasons. So in this case, welding is very costly, because when you weld a pressure vessel, it needs heat treatment and all this sort of stuff before it can be used again. So what they'll do is instead, they'll use internal piping and post networks to avoid the welding and to repurpose the vessel for whatever your needs are. Like here, they've added more trays, and they just use posts instead of welding the new rings to the side of the vessel. They'll just use posts to prop them up around. Does that make sense? Okay. Oh, and in the case of where they might need to move the feed, they'll actually just run a pipe up or down and squirt it in at whatever level they've calculated to be optimal. Levelness is another issue. Obviously columns are huge, and they're fabricated in pieces. They're used over time. They settle. They become not perfectly straight. The problem being that when you have a column that's not perfectly straight, you also have ring and tray assemblies that are not level as well. So it's been demonstrated over and over again that this can have a significant effect on tray efficiencies, and it can create situations where the malperformances, make it impossible to reach the targets of performance. The interesting thing is that towers that are off vertically by just 1 degree is discernible from 100 yards away. So, I don't know, I found that interesting. So, next there's gamma scanning. And basically the idea is, it's not so important to really understand gamma scanning per se, it's just to understand that there's another layer of complexity. Before you would start any evaluation of revamp work, you would want to do a gamma scan of the entire system, both column and ancillary equipment, while it's processing at flood point conditions. And flood point conditions is when you're reaching a point where the liquid and the can no longer, the flooding point. It's when the liquid the vapor cannot come up past the liquid. So you have a point, then you can literally define a point in the system where you're getting liquid accumulation above it and liquid starvation below it, because they're just no longer moving swiftly by one another. It's really important to understand this, because you can spend a ton of money and a ton of effort replacing internals, which would, solve any hydraulic bottlenecks in this area, and then just find out that it's your ancillary equipment that really had, or in combination, was creating, the bottleneck situation. So it's pretty important it's a very complex process, and it's important to know exactly what you're dealing with before you get involved. Larger columns present a whole nother layer of complexities, mainly, a lot to do with their size. If you take a diameter of a tower and you double it, you actually increase the cross-sectional area by 4 times, right? So this can create a lot of issues with achieving the optimal liquid-vapor distribution. You can also have the froth flows, which will become harder to control, so you may have flows moving in directions that you don't want them moving, things like that. So it just becomes another layer of complexity. Also, there are tide marks that need to be paid attention to. When you disassemble, the reboiler and the columns, you need to look for things like this, because where you can see the ring there, that actually indicates metal thinning due to corrosion. So it's something you couldn't really plan on. You really can't know that till you open it up and you see where the froth levels were and the height differences between them and whether you actually have that corrosion. But obviously once you see it, you need to deal with it. And so it makes it harder to plan and budget the process. So finally, you have a final post-revamp inspection, which would go down pretty typically, I think. I mean, what you might imagine. The final inspections, they all happen before you close the thing up and make it ready for use. The team of inspectors would include someone, these are usually done in teams and subcontractors are involved. There are teams of engineers that specialize just in revamps. So the person who owns the column would ideally have a person on the team. And then, of course, all the findings would be thoroughly documented, as you might imagine, with inspector names and dates. Safety considerations are obviously very important. You're not going to spend all this time and money revamping a column only to have it blow up or do something really not intended. So as always, you have safety, this is part of a safety culture now pretty much anywhere you go. They want your input, you have to be paying attention all the time, and making observations and being very aware of your environment. Of course, you're going to observe OSHA standards. I mean, most places aren't going to give you a choice in that matter. And then these are just some examples of typically used, policies and procedures that you can tell by the names. It's really just an example. You can look and see that these are all designed to be checks and balances. It's just layers of things in place to make sure that everything is safe. Finally, I just wanted to highlight that the CSB, or the U.S. Chemical Safety Board, is a really great resource if you're not familiar with it, for data and analysis regarding the chemical process safety. They analyze a lot of the landmark cases of accidents, and actually just last month they issued a safety memo in commemoration of the BP Texas City refinery explosion, which happened in 2005, which I thought was good because it highlights, these seem all like things that are very no kidding, right? Like, of course, it seems all very common sense, but we still have ongoing issues with safety. And in this particular accident, it resulted from the malfunction of a very neglected column and its associated ancillary equipment. And it just highlights the necessity for timely and well-executed internal and external revamps. So the take-home message is the columns are ubiquitous in chemical separations operations. Many of them are aging and in disrepair. You're likely to run into this problem if you go out into industry. Obviously, these timely and well-executed revamps are critical to production, efficiency, and maintaining a safe work environment. No two column revamps are the same. There are many opportunities for complexities to arise. So every step of the revamp process has to be accurately and thoroughly analyzed. And thank you for your time and attention. And are there any questions?